The broadcast is now starting. All attendees are in listen-only mode.
Sound check. Testing sound. If you can hear me, please click on the hand button. Thank you. We'll be starting the webinar in a few minutes. Just waiting for a few more people to arrive. And we'll be starting right at 8 o'clock Pacific time. That's in about 8 minutes. Today I'm going to talk about doing a time series analysis in GoldSim, and we'll cover a few different functions. There are many more things you can do with time series analysis, but I think this gives you a pretty good overview of some of the things you can do with time series in GoldSim. To start off, I wanted to show a couple of photos. So let's see if you can see this. This is me climbing Mount Rainier. I just climbed this past weekend, and here we are at the top. And I wanted to show this because I decided to use, for the time series data, the White River, which drains from a glacier up on Mount Rainier. So that's what I'll be using for demonstrating the time series analysis. All right, so you should see my screen now. It's a GoldSim model that says time series analysis at the top. And like I said, if you have any trouble hearing me during this, please let me know. So what we're looking at right now is 3 time series in GoldSim. We have river flow, and if I open up the properties of this, you'll see that I just pasted in the information from the website that I obtained the data from, in this case the USGS water data that they have available online from their various gauges. In this case, it's the Headworks flume near Buckley, Washington. And I have flow units here, and you can view the data here. All I did was just copy and paste it from Excel. Now, there's one thing I need to make sure you understand is that I have slightly modified the time series because there were days when the recorder wasn't working and it just went to 0. So you'll have to deal with that before putting it into GoldSim. I would suggest doing that anyway. Now, there are probably things you could build in a model that would allow you to interpolate, but I didn't do that in GoldSim. I did that in Excel before pasting the values in here. Obviously, that's going to present some errors because you can only interpolate so well. You don't know exactly what happened during the time that it was shut down. So anyway, those things need to be dealt with. Same thing for temperature and dissolved oxygen. These were also taken at a nearby location to where the flows were recorded. So you can just right-click on these time series and plot them over time. This is also part of time series analysis, just viewing the data itself and looking at it, checking for problems that you might see. In my case, what I saw were periods in which the values were exactly 0, which raised a flag for me, and that's when I went back and fixed some of those values. Okay, so you might also have some outliers. Anyway, some of those things need to be fixed. Here's the dissolved oxygen. You can see that around 2015 there were probably some issues there that you may want to look into. Anyway, this is all part of time series analysis. Just running the model for the duration of the historic record that you have, and visualizing it in a time history plot. I would say this is part of time series analysis. Okay, so this is good. Just being able to visualize it simply by running the model for the same duration as the dates, starting date and the ending date of your time series. So to do that, just to review, I go up here to the simulation settings and make sure that the start time and the end time correspond to the historic record of our time series. And then you can just add a plot and view that information. Another thing you could do is view over time two variables. So in this case, temperature and dissolved oxygen. I could view them at the same time. And when doing this, you might see there is a correlation here. We'll talk more about correlation and actually doing something about the correlation. But here visually, we can see there is a negative correlation. When temperature is high, dissolved oxygen is correspondingly low. So we want to take that into consideration. Okay, so with that, I'll go to the first analysis type, and that is using reporting periods. Click Save here and open, and go to reporting periods. Okay, so here is the same data, but what I have done is I've set up major and minor reporting periods for annual and monthly periods that I want to aggregate information and view statistics on those reporting periods. So this is something built into GoldSim. We don't really need to do anything extra besides setting up the simulation settings to have these reporting periods. In addition to that, at the result element, so if I click on this result element that is linked to the time series output, I can then choose a time display setting in the chart properties here, and choose, instead of simulation time, choose reporting periods. Then I will have the ability to look at a specific statistic of that reporting period. So for example, I might want to compare the flows at all the points to the cumulative values or cumulative flow or volume of water that flowed past that site for the duration of the period. So let's say the monthly volume of water that flowed past that point, and compare that to the daily flows. If you wanted to do something like that, that's very easy to do with reporting periods. You could also look at averages over those periods as well. So when I run this model, now I can look at the flow rate and compare the daily values to the monthly the monthly volumes. Okay, hopefully everybody can hear me and see the screen okay. It looks like there's no problems. All right, now with temperature and DO, the nice thing about using reporting periods is that you get a better idea of what the correlation between the two variables are. By looking at the reporting period results, it takes out a lot of the noise, so it makes it a lot more clear to see how the two variables compare. Also, annuals, you can see that they are somewhat correlated here. Okay, so reporting periods is definitely useful for aggregating your results. You can also use reporting periods to look at reporting period statistics using Monte Carlo simulation. So let's go ahead and do that. It's a similar model to this one, but I've added one more layer to it. So I'm just going to save this, open reporting period statistics. Okay, so now what we're doing here is we have the same data set. If I open up the time series, you see it's the same duration, June 2010 all the way through 2019. Okay, so that's the same. One thing we're going to change, however, is we're going to run the model for just a single calendar year. So if I look at the simulation settings, you see that it's running for 365 days, and it's running for a in this case, an arbitrary year, and I just chose starting 2019. You can choose any year as long as it's just a year if you want to run a model that looks at a typical year. That's what I want to do now. And then I want to run it for multiple realizations. And I want to walk through the time series starting at on the first realization. I want to start at the beginning of the time series. On the next realization, I want to go to the following year in the time series. On realization 3, I want to go to the third year in the time series, etc. Okay, so to do this, first I have to set up Monte Carlo simulation. So go back to the simulation settings, go to the Monte Carlo tab, and set up the number of realizations that I have, number of years in the data set. In my case, I have 9 years of data. So I'll run the model for 9 realizations. It would be nice if I had more data than this. So in your case, if you're doing this kind of thing, hopefully you can get more than 9 years of data. But anyway, I'm running this for 9 realizations, and then I'm going to do what's called time series shifting. So in your time series element, if you go to the properties, you'll see that there's a more button down here. If you click on it, you'll see there are these additional options near the bottom, and the one I want to use is called Enable Time Shifting. So I check the box, I go to the settings, and you'll see that we can shift the data set during the simulation in multiple ways. One of those is to use a random annual starting point. Instead of doing a random starting point, I want to tell GoldSim where in the time series to start so that I can use the same starting point for all of my time series in my model. This is important if you have multiple time series that are coupled. In my case, I had flow, temperature, and dissolved oxygen all being recorded at the same location, so I want those to all be sampled at the same point on each year as we walk through the data set. So I'm using this variable called shift year that I created, that I'm linking from an expression element that I created here, showing on the left side of the screen. Okay, so let's look at what shift year is doing. I'll close this, go to shift year. What this is doing is it says I'm starting with year 2010 and I'm adding the realization number. When you do a Monte Carlo simulation in GoldSim, there's a run property already known called realization that starts counting an integer starting with 1. So on the first realization, this variable will output 2011. On the next realization, 2012. Since I don't have a full data set for 2010, it starts in June, I had to skip over to 2011 for the first realization. So on January 2011, it will start reading from all 3 of these time series. I know that it will start in January because if I go to my simulation settings, you see that the start time is January 1. Now I could have started this in June 1. Therefore, if I did that, then I could start reading the time series in 2010 because the data starts June 1, 2010. So just some of those things you need to think about. When do I want to start the simulation, or what month of the year do I want to start the simulation? That should correspond with the month, or it could correspond with the month of the starting point in the time series. Or you can just choose any month that you want to start it in, but you just need to make sure that when you shift your time series with the shift year, that it will pick a value that is at or after the start of the time series data. Okay, I'm also using reporting periods like I did before, but the difference here is that I'm running multiple realizations that sample each year of the time series. So now when I run this model and I look at the flow rate, now what I'm going to see is a range of flows. This is essentially the monthly values from all 9 years on record. But it's showing me a probability range for each of those months. Another thing I could do is I could look at a statistic. So this is showing me a statistic of 2 things actually. It's showing me the mean daily flow, and it's showing me the mean monthly. The mean daily, in this case, might not be as useful, but it does show me the average monthly values over time. And you could also look at a statistic. I could pick a statistic. I could say, instead of just the mean, I might want to look at the 10th percentile, which is now showing here. Or you could look at a combination of things. I want to look at the 10 percentile and the mean and the 90 percentile all in the same plot. And somebody asked, is this statistics from observed data? And this is indeed from observed data, yes. This is all from the 9 years of record that we have. That's correct. Okay, another thing we can do is look at temperature versus dissolved oxygen on a monthly basis. So this is the mean on a monthly basis. And so, like I said, we could change this to look at what's a percentile, what's the 10 percentile, it looks like this. Or we could look at a tabular view. So pretty quickly, without doing very much to the model besides just setting it up, we were able to get a lot of information about the time series. Okay, so this is pretty much where we leave simple stuff and go into more complicated things. Right now, we've been leveraging all of GoldSim's capabilities to pretty much do all of the heavy lifting for us. But sometimes we need to do a little bit more. Sometimes we need to do things at the beginning of let's say we need to pre-process a time series, and we need the results of our analysis to then run a model. You might need to do something like that. Or you might need to do a time series analysis of a model result, of a time history result in your model. So either of these types of analyses might require a bit more. So let's continue on from here. So the next thing I want to look at is doing simple statistics on an array that we've converted from a time series. Okay, so I'm going to open another model here, and going to this one called array statistics. Okay, so this is the same data again, but now what I'm doing is I'm converting the time series directly over to an array. Now, why would I want to do that? When I do that, I have access now to built-in array functions in GoldSim to allow me to do things without even running the model. So, well, in this case, you have to run the model, but you don't have to run it over time. You can just run it statically. So if I go to the simulation settings, you'll see here that it says that this is a static model. It's also not a Monte Carlo model. Static model, it just has to update one time. And when it does that one update, it converts immediately the entire time series over to an array. Now, there are a couple of things you have to know about when you do this, just because of the constraints that you're in within GoldSim. One thing you have to do is you have to create an array label set that has exactly the amount of rows in your time series if you want to evaluate every row in the time series. Okay, so you can determine how many rows are in a time series by hovering over the time series element icon, and you'll see that it says it has 3,367 records. So we need an array label set with that many rows in it. So you create an array label set by going to Model, Array Labels, and then you see I created one here. Okay, and this is an indexed array label set. So very simple, just counts 1 through that number of rows. And then what you can do is create a function or an expression that looks like this. You might notice, by the way, that the shape of this expression element property window is a little bit different than what you're used to. I'm using a future build of GoldSim that is going toward our next release. So a few things might look a little bit different. All right, so what I'm doing here is I'm doing what's called a vector constructor. A vector constructor is a built-in function in GoldSim that's just vector with parentheses and you put something in there, what you put in there will be what is needed to build the array. So in our case, the result is going to be units of CFS for flow, and the type will be my new vector called TS rows, which has 3,367, actually 3,366 rows in it. And then what we're going to do is we're going to refer to the time series and call this variable row. This means it's doing, essentially what it's doing is a for loop over the array where row increments, this variable called row, it increments on each step as it walks through each row of the time series. So on the first row, when row is 1, then this thing will evaluate to row minus 1, that's going to be 0 times days, that's going to be 0 days. So that will look at the first row in the time series. This next argument, 2, means that we're not looking at calendar times of the time series. Rather, we're looking at elapsed time of the time series. Okay, so this makes it nice because I don't have to worry about dates. All I'm doing is starting on the first time point of the time series. One thing you want to make sure of when you do this kind of thing is that you want to assume that the time series has equal time points in it. So it's not missing dates, for example, in there. If I open up the time series, then, and by the way, if you were missing a date, then as you build the array, it would just interpolate if you're missing dates, just FYI. Okay, so if you look at the data, you'll see it's calendar based. But what we're doing is we're using a time-based lookup. And so 0 days would be the first row. 1 day would be the next row because that's June 2nd, if that makes sense. So that's why I have this 2 in here, because when you do a lookup on a time series, the second argument is optional. And if you put a 2 there, it means it's going to do an elapsed time lookup, which is what I'm highlighting right here. That's the elapsed time in the table. So essentially, this row value just increments immediately as soon as this vector function is called. So this vector function is called at time 0, and it immediately begins to increment. And as it increments, it appends to the array, which is this output, this main function here called river flow values. And once that's done, then we can calculate other things now that we have an array. So if I run this model, what you'll see here is if I plot an array view plot of this array, it will look just like what you saw for the time history. So if I right click array, you'll see this is a bar chart. I know it's not very useful to look at, but generally you can see that the bars coming up are what we saw earlier in the time history plot. Okay, but with that, now we can quickly calculate things like what is the mean over this time series? What is standard deviation, min, max? All these things are built-in functions that we have access to. You could do the same thing with other outputs as well. Okay, well, now we have a static model, but in your case, you might want to run a time-based model. Well, this is the kind of thing you might want to do in a submodel, for example. You might also just do it in a container that is conditional, that only runs at the beginning of your simulation. So you don't have to repeat these calculations over and over. So to do that, let me just show real quick what I would do. I'm going to save this. I won't save it after putting a container in here, but one thing you could do to save time in your big model, if you were to use this approach, would be to make sure that array function only happens one time, just at the very beginning. There's no reason to repeat this calculation. In case you have a large time series, it might be an expensive calculation to make. So what we can do is drag all of these expressions into the container here, and then we could go to the properties of the container and select conditionality. Go to the conditionality and activate this container so that it only happens at the very beginning of the simulation when the model activates, and then make sure to deactivate it on e time when e time is is, let's say, 1 day. So it'll deactivate at that time, and then that would save you some runtime if you wanted to do a simulation over time, but still access things like a statistic of the time series. Okay, so this is a way to generate an array from a time series. There's one more flavor of this kind of thing. We already have this in our library, and what it does is it takes from a time series just like this, it builds seasonal arrays and annual arrays. So you might want to look at things like, what is the average for January in all the Januaries in my time series record? If you wanted to do something like that, then you would go to our model library and download a model that's called, hold on one second, monthly annual totals. So this model you can find in our library, like I said, and I do plan to put some more of these models I'll be showing you today in our library later on. But this one is nice to have because you might need to, like I said, know what the monthly averages are at the beginning of your simulation from your time series. And if you go into the array calculations, you'll see there's a bunch of stuff going on. Don't worry so much about it. Essentially what it's doing is it's using discrete change elements to build the array as it walks over the time series. So the important part that you need to know with this model is that it's walking over the time series over time. Okay, so this is not a static model like the other one was. If you go to the simulation settings, you'll see it runs for a duration of time. In this case, we're looking at a different data set that runs from 1948 to 2018. But anyway, what you need to know about this is that these functions require that the simulation runs for that duration. So if you wanted these values at the beginning of your model run, then you will need to put all of this into what's called a submodel. And by putting this into a submodel, then you can expose these outputs, for example, the monthly averages, on the interface of the submodel, and have the submodel run at the beginning of your main model, and then you would have access to these values for the duration of your main model. If this is something you want to do and you're struggling to implement it, please just let us know. You can go to support.goldsim.com and ask us a question there. I would be happy to help you construct that or design that implementation. It's pretty straightforward once you understand how a submodel works. Okay, so when I run this model, then what we can look at here is both the time history of daily data. This happens to be precipitation in Salt Lake City, Utah. We can look now at monthly averages as an array, bar view chart or table, and other statistics that are seasonal and annual. Let's see, I think, yeah, that's annual. Oh, here's a table of monthly and annual. So years by month. So you can imagine some of the statistics you could do on this array in GoldSim now that you have those arrays available. So that could be quite useful. Okay, let's move on to, I have a few more things I want to show, so I don't want to spend too much time on this thing. Let's talk about using Monte Carlo simulation to come up with a distribution in multivariate for time series data. So I'm going to another model, and in this case, we're going to look at a distribution. Let's see, time series distribution. Okay, this is a very simple model. We're using the same flow data I was using before. And now what we're going to do, instead of converting the time series to an array, now I'm going to convert it to a distribution. Well, actually what I'm going to do is I'm going to sample each row's value on each realization of the simulation. So again, I need to know how many rows are in the time series record. In this case, I have 4,779. This is different than the other time series we were looking at. Oh, I didn't put the note in there, but this one is actually flows for a different location. But anyway, what we're going to do now is I'm going to set up the model to run Monte Carlo with 40,779 realizations. So if I go up here to simulation settings, go to Monte Carlo, and you can see we have that many realizations that we're going to run. It's also a static model. There's no reason to run this over time because all I'm doing is grabbing each row successively through the time series on each successive realization. When I run this model, what I get here is a distribution output because the expression here is a lookup again on the time series. This time I'm doing it by realization, not by row. So I say on realization 1, subtract 1, multiply it by a day, and again that's the elapsed time in the time series. And when I go to realization 2, that's going to be 2 days. That's going to be 1 day. Realization 3 is going to be 2 days into the time series, etc. Now by doing that, I've come up with a distribution. So this is a distribution of all the flow values in the time series record. You could look at a table of all those values as well. This table should correspond exactly to the time series record. So 98, 92, 90, 98. So those are the same exact values, just walking through each row. Now, why would we want to do this kind of thing? The reason we want to do this is we may want to look at a pair of time series records and see how they correlate to each other, just visually. This will be very easy to do using this kind of setup. So let's talk about that. Going to open up another model that has 2 time series in there. Let's see, it's the one that's called Multivariate. Here it is. Okay. This is the data that we were originally looking at, although it's got a few other time series added in here. It has pH that was measured, conductance, and turbidity. But anyway, it's the same data set. Okay, so now what I'm doing, again, I have a static model, and I'm running this for the number of realizations that I have rows in the time series. In this case, 3,367. If I hover over my time series, you see that it says 3,367. So now we could run this model. And now what we can do, instead of just looking at a distribution by itself like this, we can look at how 2 variables correlate to each other. So for example, one thing that we saw early on is that temperature and dissolved oxygen are correlated. So now we can see exactly how they are using a scatter plot. So now with a multivariate plot, what we can do is we can visualize or we can plot 2 time series values on each of the X and Y axes here, just point by point. So this is the paired data of these 2 time series records plotted against each other as a scatter plot. So we have dissolved oxygen on the X-axis and temperature on the Y, and you can see there is definitely a trend here in the way that they're correlated. You can see that it appears they're linearly correlated. You can look at some other things. I think in our case, there was one other correlation that I was sort of seeing here. Some of them don't correlate. That one doesn't. Which one was it? Maybe it was flows and turbidity. No. There was another one that sort of correlated here, and sorry, I'm just going through each one to see if I can find it. Here it is. This is sort of a correlation here too, flow versus conductance in the river. Anyway, I chose temperature versus dissolved oxygen as one that I wanted to look at. So in the multivariate plot, by the way, if you're new to multivariate plot, you just go up here to insert a result element, and you'll see it's the one called multivariate result. And you need to run a Monte Carlo simulation to see this, and you just link to 2 separate variables to see how they correlate on all the realizations. Okay, So one thing you can do here is you can look at correlations, and that's just a button here at the top of the window here, and it allows you to see how these two variables are correlated. So you can see there's a negative correlation. You can also look at sensitivity analysis and some other things in here, but that's the main thing I wanted to show you because we're looking at correlation. But what if you wanted to calculate the correlation as a value and then use that number in your model? Well, it turns out that Ryan here in the office helped me build a script that written in C++ that allows us to connect to a DLL or connect to use the script via DLL in GoldSim, so that now we can calculate the correlation factor on the fly, which is great because you might want to use that to actually model a dependent variable. So let's go to that model. I think it's this one. Yes, okay. So now we have the same temperature and dissolved oxygen time series. And now what I'm going to do is I'm going to simulate this over time, in this case just for a chunk of the time series record. And I'm only doing it for this period because, as you saw earlier, there was something weird going on with dissolved oxygen. So I'm just picking this kind of short period where I didn't see too much problem in the record. And let me plot that just so you can see. We plot temperature versus dissolved oxygen. Okay, there's a little bit of a problem over here in October 2015. There may be some others, but maybe one over here in early 2014. But anyway, for the most part, it looks pretty good. And so there were some other parts like later in 2016, or no, earlier before 2014 actually, where I had to do a lot of interpolating, and it just wasn't a very good period to look at. So I'm just focusing on this part of the record. And when we run this model, this is an external element right here that is calling this DLL that Ryan compiled for me. And what it does is, as it walks through time, it calculates a correlation between these two variables. So it doesn't matter how long the simulation is. This is the great thing about this DLL, is that I don't have to build an array that has exactly the number of rows that are in this time series. I don't have to worry about any of that. I just put this in here, I make sure I have the DLL in the same directory as my model, and then I just run it, and it calculates over time the correlation. In fact, you can see that the correlation coefficient is changing over time, and it gets smoother and smoother until finally it uses all of the values in the time series and returns this result at the very end. So now it's showing me the final value of the correlation is negative 0.88, and it's a little bit different than we saw before. Before we saw 0.9, negative 0.9, but I'm only using a fraction of the time series record. Okay. Also, what Ryan added to this this cool DLL is slope and intercept, assuming a linear regression of the data sets. And with that, now we can build a model of what I'm going to consider to be the dependent variable in this model. What I'm saying is that dissolved oxygen is a function of the temperature. It's kind of my assumption I'm making. And so now, instead of using the time series, let's say we didn't have a very good record of dissolved oxygen for the entire simulation, or maybe going forward in the future. Rather, I want to model it, and I'm going to model it assuming a linear correlation between temperature and dissolved oxygen, which we kind of see, in our previous analysis. So what I can do now is I can use these values of slope and intercept. This is for a linear regression, for creating an equation to model the dissolved oxygen. So now I have this element called DO simulate. It's just an expression that takes the slope value from the correlation and multiplies it by my independent variable, in my case, the temperature. And then I add to that the intercept, also taken from the DLL. And now I can essentially simulate a model the dissolved oxygen. And now when I plot this, it starts at 0, so you can ignore that first time step. But you can see here that we get a pretty close model of dissolved oxygen over time that is similar to the measured dissolved oxygen. So the cool thing about this is it's a function only of temperature. This blue line, and we used the correlation coefficient from the data sets. But now what I could do is I could run this model for as long as I want, as long as I have a temperature input. Then I could estimate dissolved oxygen over time, which is nice. If I didn't have that data available. So this is a nice thing that you could do using correlation. Okay, I want to cover 3 more things. The next one is autocorrelation. So autocorrelation is looking at how a single time series corresponds on a daily basis to its previous value, or some lagged value. It could be not just the value on the previous day, but maybe 2 days ago or 3 days ago, some period of time that's lagged. And if you want to do that kind of a correlation, then that could give you information about the randomness of your data. And so let me show you that example. So let's see, autocorrelation. With autocorrelation, I'm going to need an array. Now we could do this in a similar fashion with the DLL. What I'm doing in this case is I'm just converting the time series to an array, and I want to do that because I need to walk over the entire time series and look at its current value and a lagged value, and then based on those, I can calculate the autocorrelation factor. So I'm using a conditional container because I only need to do this at the very beginning of the simulation, but the simulation might run over some period of time. Okay, but I can calculate immediately the autocorrelation factor by walking over the entire series at time 0. So that's what I'm doing here. If I look at the container conditionality, you see it activates at the very beginning, and then it deactivates after time 0. Okay, so inside the container is just a script element. And the script element, it's doing the autocorrelation calculation, which is just put the time series into a vector and walk over the vector and calculate the lagged values and put those into a separate vector. And then looking at those two, well, first we calculate some statistics, and then we walk through again, and we calculate this these two variables that then allow us to essentially get to the autocorrelation function. I did put a reference in here you can click on to see what I'm doing or why I'm doing this. But anyway, so you come up with this this thing called ACF, and that's the autocorrelation function, and that's an output of the script right here. So when I run this model, we see that autocorrelation is 0.98. That's pretty good. That's pretty correlated. What that means is that if we're looking at just the randomness from day to day, let me just zoom into a spot. What this means is if we were to compare this line to an average or a smooth line over time and see how it's jumping up and down, if the number, the autocorrelation number, is closer to 1, then as it approaches 1, this line will become more and more smooth, and it will also stay high longer and stay low longer, so it will have valleys and peaks that last longer. If it's 0, then it will be totally random, just up and down. And then if it's a negative number, then it will be inversely correlated, and therefore be trying to be the opposite every time. Or if it's high, at one point it'll be low on the next point. That would be a negative autocorrelation. Okay, but anyway, why would we do something like this? Why do we need this autocorrelation number? Well, it could be that you want to generate a new time history, or you want to model something in like say temperature, based on statistical analysis of your time history or your time series record. And so in order to do that, you're going to need a couple more things in addition to autocorrelation. You're going to want to know seasonality and trends. So those are some other things that we'll have to calculate. Let me just talk briefly about both of those. Let's go to looking at seasonality in GoldSim. Save this and go to a new model called seasonality. Okay, there's a lot going on here. I don't want to get too much in the details because we don't have a lot of time. But what I do want to show you is that I'm just using a submodel to calculate generally how the seasonality looks for this temperature record. And so when I run this model, I'm just going to run it for a single typical year. Even though this time series record has many years on record. In this case, it's temperatures in Salt Lake City, and it's from 1948 to 2018. Okay, so when I run this model, in fact, before I run it, right now it's running for multiple realizations. Let me just run a single realization to keep things simple for now. Let me just do that. Okay, so here is a single realization of temperature over time. It's just one of the years on record. And it turns out that I'm using shift year again, starting at 1948. So this happens to be 1948 on record. Okay, you can see that it does have some seasonality to it. It kind of drops a little bit, then it rises up until July, August, and then it drops back down toward January. So if we were to simulate this over multiple years, then we would see a similar type of pattern. Let's go ahead and do that now. So I'm going back to Monte Carlo, and I'm going to change it to run for 68 realizations. The reason it's 68 is because I have 68 years of record. Let me just make sure I have everything I need in this before I run it. Okay. All right, so now I'm going to run this for all the years on record. And I just want to look at temperature, the time series temperatures. So just bear with me for 1 second here. Okay, here's the temperature. So this is a range of temperature over all of the years on record, right? I can look at a single realization and just focusing on the red line, that is let's start with realization 1. Okay, this is 1948, 1949, 1950, etc. That's the red line. And we can see that there is a seasonality to this. Like I was saying before, obviously it's low in January, it rises up to a peak in August, and then back down again. How did I get that blue line? That blue line is showing me the seasonality of this time series. The way that I got this is by using a submodel here. The cool thing about the submodel is that it can just run one time on this definition at the very beginning, on the first realization. I don't need to run it after that. All I need to do is run it one time, and it will generate for me the monthly average temperatures. And from that, I can determine, I can visualize what the seasonality is of that time series. So let me show you how the submodel works. If I open up the properties of the submodel, first of all, the time is just running for a single year. Monte Carlo, it runs for the number of years on record. I can't remember if it's 68 or 70. I might need to change that to 68, but it's the number of years on record. And then the interface, it brings in the entire definition of the time series. That's the important part. It's not just the time series value when it runs, but it's the entire definition. If you're wondering what a definition is of a time series, let me just explain that. If you go to a time series element and you click on the output port, you'll see there are two things here. This main output is its current value. Well, that's not what I want. That's not what I want to pass into the submodel. I want to pass the entire time series record into the submodel. So I'm going to refer to the definition. That's the entire set. Okay, so in the interface here, I'm passing in the entire time series set. Now when I go into the submodel, now I have linked I have a linked time series. A linked time series means it's a time series that's linked to another definition. And that's done by changing the data source here from locally defined to linked. Now that that's linked, now what I can do is I can just refer to the interface of the submodel and find that output that I linked on the interface. So this is coming from the outside. I'm just passing that time series in. I could have copied and pasted it in here, but what if I needed to change it later on, right? It'd be better to link it into the submodel. Now that we're in the submodel, now all I have to do is export a time history of that. Now we could be more complicated. There could be calculations going on in here, and we could export some output, but in my case, it's just simply reading the time series, but it's doing it in a specific way. If you look at the time tab on the submodel, you'll see that we are saving results for only reporting steps. And I'm only doing major period steps, which are monthly. Okay, so that means it's going to look at the monthly values of the time series inside of there, and it will export them, and I can look at a statistic of those monthly values. In my case, I want to look at the average. Well, I'm actually looking at min, average, and max of all the months of all the years of record. So I do that on the interface, on the output interface. So in this case, I'm going to refer to the time series as a time history, but it's a statistic history. So I'm looking at all the years on records. Let's say we have 70 years. I'm going to take all 70 years, and I'm going to calculate the mean of those 70 years, but I'm going to do it on a monthly basis. And I'm going to expose that on the output side and link it to another time series that I can use in my model. So now, with all of these runs that we're doing, that we're looking at, the temperature, now I will have a constant average monthly value. So I can look at that as the seasonality of my temperature. So now you might be wondering, okay, well, I have the seasonality, now what am I going to do with it? Well, now what you can do with it is you can model temperature. Instead of using your time series, now what I can do is I can use a stochastic that takes the average, the seasonality essentially of my time series record, in my case the average temperature, and I can build it. I can synthetically generate temperature values now. So if I go to the stochastic here, click on edit, what I'm using is a triangular distribution. Now this is just something I've assumed, but you'd probably want to do more analysis on the monthly values than what I've done. But essentially I'm just saying that I have a most likely value of the average temperature, and then I'm going to range that from the min and the max, which are also calculated in the submodel. And now I'm going to simulate my own temperature amounts. And I'm going to resample that every day and come up with a new value. So I'm essentially modeling temperature now, just using the seasonality values that we calculated using the submodel. And then there's one last thing, and that is that we don't want it to be totally random. We're going to autocorrelate when we do the sampling. So for example, if I picked, let's say, a high value on this distribution on one day, let's say 55, then if it's autocorrelated, then you should see on the next day that it would also pick a number fairly high on the distribution. It won't be random from day to day if there's autocorrelation. We've already determined that there's autocorrelation. I've done this autocorrelation calculation in the previous example, but now what we can do is we can link the autocorrelation value using autocorrelation in the stochastic to then drive a temperature value over time. Run this model again. So now we can look at temperature over time using the stochastic and look at single realizations and see how there is autocorrelation in the amount of time or over that period of time. So that's how we're using autocorrelation in this case. Okay, one last thing I wanted to talk about. We have a little bit more time, and that is trend. I'm just going to show a real simple example. There's a lot more we could do with trend in GoldSim, but let me just show a simple thing that I'm doing here. I'm using an integrator to calculate the trend, and I'm doing that by integrating the time series value and then also using an advanced option on the integrator called the calculating the moving average. And I'm using a 10-year moving average to estimate a trend in the temperature over time. That's all I'm doing. So now when I look at the time history, you can see that we have the temperature changing over time. This is over, I'm looking at annual periods here. And then the integrator is calculating on a daily basis the 10-year moving average. And so with something like this, you could see near the end of this run, you could see a moving average that you could use as a trend going forward. If you were to say, I want to use this as my average annual temperature value, and I want to continue with the trend that's been going on for the last 10 years, then you could just run a line that has the slope that we're using here. So that's something you could do with this model, is you could look at the slope of this trend line and continue that forward if you're going to do a forecast of temperature. So now we have all the parts we need to simulate temperature going forward in this model. We have the trend, we have the seasonality, and we have the autocorrelation, all taken from an analysis of the time series. So that concludes the presentation. I hope it was useful. I'm going to spend a little bit of time on any questions that you might have. Thank you for joining. I will put the video recording on our website, and also I'll make the models that I'm using here available for your use. Thanks again for joining. I hope it was useful.